Okay, so chapter 15 deals with correlation. It's a statistical technique used to measure and describe a linear relationship between two variables. Some things to note: that the variables are not manipulated. It requires two scores for each individual. So you have an X variable and a Y variable, and there isn't really an independent and dependent variable in correlation, so they're just X and Y, and it doesn't matter which one's which. You list it in a table or as a scatter plot, and it's sometimes referred to as the Pearson product moment correlation coefficient, and it's denoted with the lowercase r. There are correlation coefficients for nonlinear or other types of relationships, but we're going to just cover the Pearson linear correlation coefficient here. So the requirements are that you have a sample of paired data that come from a simple random sample of quantitative data. So you have an X and Y for each individual. Visual examination of the scatter plot shows that there's a linear pattern. And just a note about bivariate normality: as at a fixed variable of X and Y, data are normal and vice versa. We will just assume normality for a sufficiently large sample, for example, greater than 30. And then also outliers radically affect the results. So we want to check to make sure that there aren't errors if you do have outliers. Some characteristics of correlation. The strength of the relationship has to do with the magnitude, not sign. So a correlation of negative 0.87 is stronger than 0.80 because the number is larger. You don't need to worry about the sign. And it spans from -1 to +1 inclusive, meaning it can be 1, but it can't be 1.1. So if all values of either variable are converted to a different scale, it doesn't change the correlation. They're interchangeable, doesn't matter which one's X or which one's Y, it doesn't change the relationship. And then the sign of the correlation does denotes direction. It does not denote magnitude, and it's a linear form. So here's some examples. Here we have a correlation coefficient of almost 0.9. It's pretty strong and up and to the right. It's positive. This one's pretty strong. It's almost -1. It's down and to the right, 0.97. And you can see this is a more disperse line, which means that that's why it's slightly less value than this one. Even though it's negative, you can see it's pretty hugging tightly around that line. Here we see no trend, and so we have almost a 0, which is no correlation. And then here we have a curvilinear relationship. So it still has a correlation coefficient because it's still trying to fit a straight line through these data, but it's pretty low. And if we had inspected the scatter plot, we would see that there's actually a curvilinear, and we would want to use a different correlation coefficient. All right, cautions. Remember, correlation does not imply causation. Values can be affected by the range of scores. Values can be affected by the outlier, and it should not be interpreted as a proportion. So, for example, what is my research question? Is there a relationship between test scores and the quiz scores? So here I have test scores, and here I have quiz scores. You can see this is 1 to 10, and this is likely 1 to 100. So we go to the scatter plot first. There's several ways to do this. We're just going to do the graphs, legacy dialog, scatter dot, pick simple scatter, click define, move over the variables, and click OK. It doesn't matter which one goes where. We can see we only had 5 values. Well, we had 10 scores, but 5 for each, 5 individuals. And so we have this person got almost a 7, and 50, probably like 58. All right, this person got 8 point something and 80 point something. So each dot is one person and their value on this score and on that score. With such a small data set, it's hard to tell what's going on. Mentally, I try to draw a line through the data. And so I used SPSS, I cheated, and you can see that it's hugging, that what it does is it tries to find the least the line of best fit, so the least amount of distance between each point to the line. But this guy is messing things up for us. We can see we have an outlier. Let's see what our coefficient is, but first we go through the steps. So step 1, we ask the question, is there a significant relationship between the test score and the quiz score? The null hypothesis is that there is no relationship between test score and quiz score, and the alternate is that there is a relationship between test score and quiz score. We used to use the Greek letters, and this is a Greek letter, lowercase r, so it's a row, but we're not going to do these anymore. We're just going to write it out in words. One note about degrees of freedom. The hypothesis test has degrees of freedom defined as df is equal to n minus 2. So in a sample of only 2, they both sit directly on the straight line, so there are no degrees of freedom, and the correlation coefficient would be plus or minus 1. Because the first 2 points present a perfect correlation, the sample correlation is free to vary only when the data set contains more than 2 points. Thus, degrees of freedom is equal to n minus 2. So SPSS won't give that to you when you report it out in APA. You have to just subtract 2 from the sample size, and you have to remember to do that. So, okay, when I've jumped to calculating the test statistic, but we know that our alpha level is set at 0.05. So we did analyze, correlate, bivariate. You'll have your list of variables here. You just pick the 2 you want and bring them over, and that's all you have to do. It's already collected Pearson, and it's already going to flag significant, and it's going to do two-tailed. So here we have it. Set the alpha level, compute the test statistic, and then state our conclusion, and then the results in APA. You can ignore the AMA. Okay, so remember for correlation, degrees of freedom is n minus 2, so we have to subtract 2. So we report the degrees of freedom here. We had n is equal to 5, so our degrees of freedom is equal to 3. Our correlation coefficient is 0.405, and our p-value is 0.499. Now, this is a weird correlation. It's a matrix, right? So because it's a matrix, the line of 1s here, this on the diagonal, show that the variable is being correlated with itself. So test score correlated with test score is going to be a perfect correlation because it's correlating with itself. Similarly, quiz score with quiz score is going to be perfect correlation. And these are the mirror image of each other. So because of that, and we're only doing 2 scores right now, all you're going to do is report it like this. But if you had done multiple correlation coefficients, you would want to present it in a table, and I'll show you that on the next page. All right, shameless plug. This is a paper that I did with my advisor from LSU. And you see that I only report things on the diagonal. So these are a bunch of benchmark exams that we gave throughout the course of the school year back in, I don't know, 2000, probably 14 or 15. Got it published in 16. And this was for science, and this is for social studies. You can see the APA, how I set this up. I made this table. And you can see that everything's on the diagonal. So I have CCM fall with winter. I just took out the row where it's correlated with itself and started with the next row. So you can see I have everything on the diagonal. I could have done it where I had science on the upper side and social studies on the lower side, but I like this visually. It's easier to look at. But there's many different ways you can do it. Anyway, so you can see that I have these, I make the note. So A is not significant. These guys are not. Everything is significant at 0.101 except for the ones with the stars, which are at 0.05. So this one, and then these guys. All right, so we talk about the coefficient of determination before, r squared. It's a different effect size. Since correlation should not be interpreted as a proportion, we can square it to get the coefficient of determination, which can be treated as a percentage. We've talked about this already. It measures the proportion of variability in one variable that can be determined from the relationship of the other. We just square the r value and multiply by 100. Even though it wasn't significant, I'm still going to show you with this example. So I take 0.405 times 0.405, and I get 0.164 multiplied by 100, and I get 16.4. So this works just like the eta and the partial eta squared interpretation. 16.4% of the variation in test score is accounted for by quiz score. So the final write-up. I'm showing you how to do the whole thing, but you wouldn't calculate the r square in a paper or study if the correlation was not significant like we have here. I just want to show you the whole thing. So results indicate that there is no statistically significant relationship between the test scores and quiz scores. R of 3 is equal to 0.405, P is equal to 0.499, R squared, coefficient of determination, is equal to 0.164. If it was, we'd say therefore the 16.4% of the variation in test scores is accounted for by a quiz score. Okay, now for chapter 16 it gets pretty complicated, but I'm only going to have you do this in the homework one time, and I'm going to show you how to do it. But this is simple linear regression, and it's called simple because there's only one independent variable. Okay, so now in linear regression, it's the statistical technique for finding the best fitting straight line for a set of data. I already showed you this when I showed you the scatter plot for the previous example, and then I said I mentally draw a line. I do that because of linear regression. In it, now you do have an independent variable, which is also called the predictor or the explanatory, and you have a dependent variable, which is also called the criterion or outcome variable. Linear relationship can be explained by this equation. So if you remember from algebra, y equals mx plus b, that's the slope equation, but in statistics we write it like this. Y hat, which this little hat here is difficult to make in PowerPoint, so I'm only going to do it once, but this is the predicted y is equal to beta naught plus beta 1 x, where beta naught is the y-intercept and beta 1 is the slope, and the y hat is the response outcome dependent variable, and x is the explanatory predictor or independent variable. And I'll go over this more. So if we know someone's height, can I predict their weight? We say we regress weight on height, regress y on x. If I know your score on a test, can I predict your score on test 1, can I predict your score on test 2? Well, we can't just make predictions out of the air. We do this by taking a complete data set for whom we have 2 scores. So we have 50 people, and I have their height and I have their weight, right? So I'm not predicting their stuff, I'm using their stuff to predict future people. So if I have 50 people for whom I have height and weight, and I create this actual regression equation, prediction equation, then if somebody else walks in the room and they say, hey, what's your height? I plug it into this based on my sample, and then I can predict their weight. But I'm not going to Vegas and predicting willy-nilly. I'm doing it based on a complete data set for whom I have both measures. Okay, so the line of best fit through the scatter plot. Here we have a scatter plot, and that's a pretty nice, tight-fitting line. But each of these distances is the error, right? I'll show you in the next line. So the best fit line, y is equal to beta naught plus beta 1 x. We have the measured value, we have the predicted value, and this is called error or residual. Okay, so the introduction to linear regression. How well a set of data points fits a straight line can be measured by calculating the distance between the data points and the line. Using this formula, it's possible to find the predicted value of y hat for any x. The error or the distance is called the residual. Because some distances may be negative, each distance should be squared so that all measures are positive. This is like the sum of squares we did way back at the beginning of the semester. And this is just kind of into the weeds about how this works. So it works the same way as correlation in that we need 2 scores for every individual. One score is the x predictor score, and the other score is the y, the predicted or criterion score. Now it does matter who is x and who is y. And like I said before, you'll see this sometimes. We regress y on x. Means you are projecting the y onto the space spanned by the x variables. There are 2 parts of a regression. Just like in ANOVA, we had sum of squares between and sum of squares within. It's just different vocabulary. Now it's sum of squares regression and sum of squares residual. And this is a little bit like the hand calculation, so I'm not going to go into it. You'll see, I'll show you in the next slide. But residuals are the difference between the observed value of the dependent variable y and the predicted value y hat. It's called a residual, and it's denoted as E for error. Each data point has 1 residual. So we can do this hypothesis testing. I'm going to spare you the details, but the output of regression is very much the same as that of ANOVA. So here we had mean square between and mean square within. Here we have mean square regression and mean square residual, where we have the F statistic and the degrees of freedom for the numerator and the degrees of freedom for the denominator. It's exactly the same, just different vocabulary. Okay, so research question 1. And I'm going to use a health data set. Does percent body fat predict body mass index? So state the null and the alternate. Percent body fat does not predict BMI. The alternate, percent body fat, does predict BMI. We set the alpha level at 0.05 and we calculate the test statistic. So we're using the body fat data set. This can get a bit complicated, but there's some assumptions that must be considered. And this is pretty crucial, because if you don't consider all of the assumptions, then the findings of your regression can be suspect. So the first one is that the residuals, not the data points themselves, but the residuals, the error values, are normally distributed. And then that there are no influential points, outliers that greatly affect the regression. Remember, correlation is susceptible to outliers, and correlation and regression are kind of kissing cousins. So the regression equation is also very sensitive to outliers. And we're going to look at this Cook's D values. Any that are greater than 1 are considered influential and either need to be removed or transformed or double checked. If you can't just, I wouldn't advocate just removing data we don't like. So you just have to deal with it, and that's why we want to check all of our assumptions. So okay, and then the last is that the residual plot, the graph of x and y to y hat value, shows no pattern in the data. So we want a roughly rectangular blob of data points within plus or minus 3 standard deviations along the x and y axes, and I'll show you what that looks like. So first, let's just do this correlation. So we check the scatter plot, and we can see that percent body fat and BMI are highly significant and pretty strongly correlated. You can see this one's kind of a problem, this one's kind of a problem, but they're still in the line. They're just kind of, these guys probably won't be influential, but this guy might. And the reason why is because the line's going to hug here, but it might get pulled slightly sideways this way, even though you can see that the preponderance of these data points are right here in this line. This guy might make that line tilt a little bit and screw up our correlation or our regression. So we'll see. So we go to Analyze Regression Linear. We move over our variables. So our BMI, we're using percent body fat to predict our dependent variable. So we move them over, and first we click Statistics. And this thing pops up, and we're going to pick Model Fit, Descriptives, Estimates, and Confidence Intervals. And then we're going to click Plots. And then this is just something you have to remember. I just always think of it as like the crisscross. So Z predicted and Z residual. We want to bring that one to the X and that one to the Y. And then we're going to click a normal probability plot and keep going. And then we go back to Save. We hit Continue, and it brings us back here. And now we click Save. And here we're just going to look at Cook's, and then we click Continue. And then it'll take us back here, and then we say OK. All right, so checking assumptions. Standardized residuals in Cook's distance. We want to see that they are not greater than or less than, or greater than plus or minus 3 standard deviations. They work like z-scores. We will get our output relevant information to calculate Cook's distance. I'll show you what I mean by that, and then we will see the residuals also in the residual plot. What it's going to do is when we click that Save button, it's going to put those Cook's values back into our data set. So it's going to create a new variable for us in our data set. So where you didn't have a Cook's line before, you will now have a variable for Cook's distance. And then we'll also see the residuals in the resid plot. So we get a lot of output. So let's begin with the residual plot. For the most part, the data behave fairly well. So here we are between plus or minus 2, and then we're out here. So 3 would be about right here, and this guy is a problem. This guy's not too bad. And then this guy's definitely a problem because that's standardized, that's 8 standard scores away. This one is beyond 3, so we have a few, but we're just going to keep going. This is the QQ plot, or our PP plot. And we just want all these data points to hug the line, and we're just going to say, you know what, that looks pretty normal, and we're going to go. So the first bit of output's nothing new or exciting. We see the means and standard deviations, we know that. it gives us correlations, and it gives us the variables that we entered. Dependent variables, BMI, and our independent variable is the percent body fat. Okay, so now we get to doing all of our interpretation. So the first thing is the model summary. And this is our R, so that's the same as our correlation. This is our R square, it did it for us. So 52% of the variation in BMI can be predicted by percent body fat. Now this is our ANOVA table, just like before, but instead of saying within, between and within, it says regression and residual. We have degrees of freedom 1 and 250, and here we have our F statistic, which is giant, and then we have our p-value, which is little. All right, so we have a lot going on here. So the first thing to look at is we know that we had a significant ANOVA test, right? So we do know that our regression equation is significant. Now we want to find out what is significant. All right, so this is our predicted change, the slope, the regression coefficient, the beta 1, which is 0.317. These t-values are the observed and p-value for each predictor, right? And they're both significant. And then these are the confidence intervals. We come down here and we look at Cook's, and it's 0.516. We're less than 1, so we're okay. We don't consider those influential points. What this means is that when body fat is equal to 0, the BMI would be the value of the constant. And for every unit increase on 1 percentage point in body fat, the BMI would increase by 0.32. Okay, so now we're going to state the conclusion and use APA. So we say, for research question 1, does body fat predict BMI? We say findings indicates that percent body fat is a significant predictor of BMI. F of 1, 250 is equal to 278.9, P is less than 0.04, R squared is equal to 0.527. Approximately 52% of the variance in BMI can be attributed to percent body fat. Examining the predictor, we see that percent body fat is a significant predictor of BMI. T is equal to 16.7, P is less than 0.01, and then you can give the confidence intervals, or you don't have to. We do this, it doesn't really make sense really to do it for simple linear regression because you only have one predictor, but when you have multiple regression, you do it for each of your predictors. Okay, finally, the prediction equation. In order to do this, we need to look at the coefficients table. So remember, parts of the prediction equation, we have y hat, beta naught, beta 1, x, where the y-intercept, the slope, the response or outcome variable, and the explanatory variable. So we write it in. We have 19.3 plus 0.317x. So based on the regression equation, what would be the best prediction of BMI for a person with a percent body fat of 25? So I just take this equation and then I throw in 25 here. So if you came in and you had a 25 as a percent body fat, I could predict your BMI. I would say 25 times this plus this, and I get 27.2. And that's how you do regression.